Hello everybody. This video is going to cover some of the equations, some of the gas laws that can be used for our ideal gases. Remember, we pretend that all gases are acting perfectly. We call those ideal. The biggest, most well-known one is ideal gas law. PV equals nRT. PIV-NERT is how a lot of people will say it. Remember, our pressure is the p-value. It is often going to be in atmospheres. Doesn't have to be, but it often is. V is volume. N is the number of moles. I also want to remind you that to get moles, you can take the mass of your substance and divide it by the molar mass. That allows you to manipulate this equation a little bit. If you know how much stuff you have and you know the molar mass, you can calculate your moles. Or maybe they gave you all of the values and you're trying to figure out what the molar mass of the substance is. So a handy rearrangement. R is the ideal gas constant. We say that's a proportionality constant. Remember, we don't have perfect combos of units, and so we often see these R values show up, these correction values, to make sure that everything works out correctly in our equation. There are different R values you can pick based on which which unit of pressure you're using. Often in AP Chem, we use atmospheres, but you should be able to convert your pressure to other units. Make sure you pick the right R value. Now, the further and further away you get from your standard conditions, remember the more and more things would deviate, but we're not going to be doing calculations when you have to account for deviations or for real gas behavior. And remember, T is temperature in kelvins, very important. This is a silly way to help you remember how you can calculate the molar mass of a substance based on rearranging the ideal gas law. From the previous slide, we had our PIV-NERT equation, and I had substituted lowercase m over capital M, and then you can rearrange. Then they will often ask you for the density. Now remember, density is how many grams of something you have crammed into how much space. So m over v is the same as density. So I can swap that. And now I can rearrange and solve for density. Or maybe they gave you the density and they're asking you to find molar mass or whatever variety of arrangements they're asking, right? That is very key. Remembering what density means. Remembering this equation can really save you a lot of time. The little silly way to remember this is that molar mass kitty, M, always puts dirt over its P. It's a terrible way to remember it, but it is incredibly effective. In AP Chem, they are often asking you to find unique things by rearranging equations that you're familiar with. So for example, all of that is simply rearranging ideal gas law. So it's hard because when a teacher looks at the list of things to teach and it says teach ideal gas law, it doesn't really stop there, does it? It wants you to be able to do ideal gas law with units that don't match. It wants you to be able to take a certain number of grams and first convert it to moles. It may ask you to find molar mass of an unknown substance or the density. And they're not wrong. It is technically just teaching ideal gas law. So making sure you're doing as many practice problems as you can to be exposed to as many unique combinations of these things as possible is really important. Now, in Honors Chem, you learned that there are other laws, like Boyle's law, Charles' law, Avogadro's law. AP Chem is not going to give you an equation and say, what's the name of this law? And technically, we don't even really have to teach them, do we? If you think about the ideal gas law, and if we're trying to compare two scenarios, we're really comparing the ideal gas law from one equation or one condition to the ideal gas law of a different condition. And if you hold certain values constant, they kind of disappear from our equation, don't they? So for example, if the number of moles and the temperature don't change, and R never changes, then you're really only talking about volume and pressure, which we give the name Boyle's law. If moles and pressure are the same, you're really just comparing volume and temperature, which is Charles's law. And if your temperature and pressure stays the same, you're really just comparing volume and the number of moles, which is Avogadro's law. I like learning the separate laws because I think in my head I can get to them faster. I can retrieve the information faster when I remember the name. But I've seen teachers who only teach ideal gas law and expect kids to be able to essentially cancel out the variables that don't change. And it's really all the same stuff, isn't it? One thing that not all Honors Chem teachers might have covered is what these laws look like on graphs. And I think that's pretty important for AP Chem. So in Boyle's law, we're comparing pressure and volume. As the pressure increases, the volume decreases, which makes sense if you think about it. If you crush something, right, it's going to get smaller. We say that that is an indirect relationship. Now, that phrase may make you think of math class, right? But it's really important that you are able to use that vocabulary, I think. Being able to explain it's an indirect relationship is a lot faster than trying to write a giant paragraph that says the same thing. Now you may notice that this graph doesn't touch zero, does it? Because are we ever going to have zero pressure applied? No, because those particles are hitting the sides of the container, which will always exert pressure. So sometimes you may be asked to explain why there's a unique aspect to the graph like this where we're not used to graphs that don't really ever touch the axis, right? So there's something to think about. I think it can be helpful to visualize pictures like this, where if your volume gets smaller, can you now see that these particles have less space? So they will bounce around and hit the container more often. And the more often they're hitting the container, the higher the pressure is. The pressure is measuring how much force is being exerted over this area. And more collisions is more force. Charles's law is about volume and temperature. Think about leaving something in the hot car. If you leave, a soda in the hot car, it could explode, right? As temperature increases, the volume increases. Your volume is going to get bigger as your temperature increases. We can see that on a graph like this. That would be considered a direct relationship. Do you notice how some parts of these lines are dotted lines? That is because they're being extrapolated. Okay, we stopped collecting data at the end of the solid line. And the dashed line is showing where we think they would finally touch that axis. We're extending our line. We are extrapolating it down and making a prediction, right? We didn't actually measure those values. Where they touch the 0 line is where they're taking up no volume, and the temperature at which that occurs is considered absolute value. We have to use a dotted line and extrapolate because everything is going to end up being a liquid before it gets to absolute 0. So we cannot take gas law equations and get gas law data and gas law measurements, right, if they're not gases. And once they become liquids, they don't behave the same way, right? So that's why these dotted lines are extrapolated. I think that is very important that you understand that when you're in AP Chem. So looking at this one from kind of the particle diagram, when they're warm, when particles are at a high temperature, they're going fast. So they're going to bounce back and forth really fast, more often, higher pressure, right? But pressure is being held constant here. So the only way to keep the pressure constant would be to allow the size of the container to expand. If the container can expand, then the distance traveled is bigger, which means it takes more time. So by allowing the container to expand, the particles have to travel further, takes longer, they will keep hitting the sides of the container at the same rate, and therefore the pressure doesn't change. So what Charles's law is doing is it's comparing the temperature to the volume. If you take that balloon and you put it into cold water, in order to keep the particles hitting the container as frequently, when they're moving slower and slower and slower, is to make them travel a smaller distance, and so the volume will shrink. That way, even though they're going slower, since they don't have to go as far, they'll still hit the balloon as often. Now, Avogadro's law is talking about the volume and the number of moles. And it shouldn't be a surprise to you that this one is a direct relationship as well. You cram more molecules in somewhere, it's going to take up more space. And we can see that in our graph. Now, if you look very closely, you may notice that when you have no moles of gas, it takes up no volume, which makes sense, right? I think being able to explain why you see those certain points or not on the graph is important. Okay, we're just filling up our space. Now there is one law that in honors chem we often present in a pretty simplistic way, and we don't get to very complicated versions of it due to time. When they changed our bell schedule a few years ago and moved us to the modified block, the way things fell on the calendar changed, and we don't have a lot of time to get into this next law very much. Dalton's law of partial pressure. Dalton's law of partial pressure talks about how the pressures of different gases in the same container add up together to give you the total pressure. Doesn't sound too hard, right? Total pressure is P1 plus P2 plus P3. The problem is it can get pretty ugly pretty fast, which is one of the reasons why it often gets skipped or not taught in depth in honors chem. So it could be a Dalton's law of partial pressure question, but they don't even give you any pressures. They could give you temperature, volume, and mole data. And you are supposed to notice, hey, I can get pressure from that. And then I can do a Dalton's law of partial pressure. That can be tough. Lots of people get to the point where, if they're given an equation, they can plug in the numbers. That's great. That's honors chem. Here's a bunch of equations. Here's a bunch of numbers. Plug them all in. AP Chem is going to take it to the next step and say, here's a bunch of numbers that don't seem like they go together. Do something with them. I promise there's always a way to do it. You may just have to think a little bit more creatively. Maybe you got to use ideal gas law first. Maybe you have to do something with density. Maybe you're going to have to do something with adding and subtracting numbers you're not used to, right? But somehow you'll be able to relate it back to the pressures. Another thing is mole fraction. Mole fraction can be a very convenient idea in several different chapters, not just for gas laws, but also in solutions. We use an X to represent mole fraction, and it's a ratio of the number of moles of one thing compared to the total number of moles present. And this is helpful because we can relate the mole fraction to the pressures once again. If you know the fraction of moles in a solution or in a gas, a jar of gas, you can figure out the ratio of the pressures for those things. So, just for those of you who are kind of wondering how this works, if we are comparing the pressure of one substance to the total pressure in the container, I can have PV equals nRT for both. And since I'm interested in the ratio, I'm dividing them by each other. You should notice that R cancels out because R doesn't change. These gases are all at the same temperature, so the temperatures cancel out. And they're all in the same container, so the volume cancels out. So by understanding what the mole fraction is, you can use that to tell you what the partial pressure ratio would be. And if NA over N total is this mole fraction thing, I can just plug that in where I see that. So once again, I'm using ideal gas law type numbers, and I'm figuring out essentially a brand new equation, but really it's just a rearrangement and understanding how we can relate these things to each other. So here is my partial pressure of that gas. And if I take the mole fraction times the total pressure, I can figure out how much of the pressure is coming from that gas specifically. So if I have a pressure of 10 and half the gas is from A, then 5 atmospheres of my pressure is coming from A. If I have a total pressure of 10 atmospheres and my mole fraction is 1/5, then 2 atmospheres of pressure are coming from that substance. You will sometimes see percentages given. they'll say you have a container at 1 atmosphere and 78% of it is nitrogen. What's the partial pressure of nitrogen? Well, remember, just turn it into a decimal and multiply it, and that gives you your partial pressure. And then you might use that answer later on. They may say if your total pressure is 1 and the pressure from nitrogen is, 0.78, your oxygen is 0.21, what would your pressure of argon be? And you can just do a little bit of subtraction to figure that out. So understanding that the pressure in a container is the sum of all the gas particles hitting means we can kind of go backwards and figure out what would the partial pressures of each of those gases be that contributes to the overall total pressure. So I hope that gives you a little bit of a reminder of some of the gas laws that we covered in Honors Chem, but also helps explain what will make it different in AP Chem. I'm not going to sit here on the PowerPoint and do all sorts of crazy practice problems, right? That's what our homework and warm-ups are for. Make sure you're doing them, make sure you're practicing them, asking questions about them. But hopefully this kind of gets your brain in the mindset of, okay, careful about units and make sure I'm substituting things, and don't forget what, I can use density and I can use molar mass and I can be creative with how I combine things, okay? That's it. I hope that was helpful. Bye, everybody.